In this section, we are going to talk about congruent chords. Now, before we get into the main two theorems of this section, I want to talk once again about distance between a point and a line. If you have a line and a point, what's the distance between the line and the point? It's the line that goes from the point to the line that meets at a right angle. Whatever distance that is, that's the distance from point P to the line L. If P happens to be the center of a circle, well, it doesn't really look like the center, so I'll just do it again. If P, the point P, happens to be the center of a circle, well then, and that's a chord. I know it's a chord because it goes from one point of a circle. It's a line that goes from one point of a circle to another. It's not enough just to go from one point of a circle to another. I just did that. Now, that's not a chord. It needs to be a straight line. If P happens to be the center of a circle, doesn't matter. The distance from P to the chord is the line that goes at a right angle. It's the length of the line that meets at a right angle. Okay, like I said, there's a couple of theorems. The first one is if two chords are congruent. Well, let's just say equidistance first. Theorem. THM is theorem. If two chords are both equidistant from the center of a circle, then the chords are congruent. Then the chords are congruent. Okay. You have a circle. You have the center, which I'll call C. And you have one chord, and you have another chord. They don't have to be parallel. Let me just move C over a little bit. If this distance and the next distance, this distance here, are the same. If those two distances are the same, and that's given, then the lengths of these two chords are exactly the same. So that's what is given. The distance between the center and the first chord and the distance between the center and the second chord are equidistant. That's why I have one slash next to them. And by definition of distance between a point and a line, we know that they meet at right angles. Now I need to conclude that these two chords are in fact the same length, congruent. So I go like this, and I go like that. Well, I know that these two are equal to one another. Oops, let me try that again. I'm so sorry. I go like this and like that, and I know that these two are equal to one another because they're both radii. Same thing down here. I go like this and I go like that. And these four lines happen to be the same. Now, I just generated 4 triangles. 2 on the top, call them 1 and 2, and then 2 on the bottom. Call them number 3 and number 4. Now, these 4 triangles are congruent. Because let's look at, say, number 1 and number 2. Okay, they both have a right angle. And opposite the right angles are the same. That is, they have the same hypotenuse. And they have a common leg. So by the high leg theorem, these 2 triangles are congruent. But the other 2 in the bottom, 3 and 4, they also have a right angle. They also have a right angle. And opposite the right angles, side with 2 slashes. And they both have a side with 1 slash. These are congruent triangles, all 4 of them. Okay, which says to me that opposite the side, the third side, this side and this side, and this side, and this side, they're the same. Corresponding parts of congruent triangles. 2 slashes, 1, 1. The third side, they're the same. Okay? So now we know that the third sides are the same. Let's label this A, B, C, D, E, and F. Well, I know that AF is equal to FB, which is equal to DE, which is equal to EC. These 4 are equal. Well, AF in particular equals DE. And FB equals EC. So if I add these, and when I say equal, you know me by now, I mean congruent. AF plus FB, that's just AB. And EC plus DE is just DC. And all of these are lines, so they get the line above them, or line segments. So AB and DC, they really are congruent. There's no way around it. They honestly are. Okay. Now, we talked about if 2 chords are equidistant from the center of a circle, then the chords are congruent. But we can reverse that. If the chords, so I'm reversing the if and then part. If the chords are congruent, then the 2 chords are equidistant from the center of a circle. That's called the converse, when you switch the if and then part. If 2 chords are congruent, then they are equidistant from the center. Theorem. If 2 chords are congruent, then their 2 chords are equidistant from the center. There's no way around it. The converse is also, in this case, going to be true. And how do I know there's no way around it? Well, I don't actually know it yet, but I'm going to prove it. So we'll all know what that is. Okay, so we have a circle. We have the center C, and we have two lines, two chords. And I am saying, these chords, same length. Say AB, CD, same length. That's given. And I modify it, the diagram. I go like this, I go like this, I go like this, I go like that. And I know one thing. Those four lines are the same length. Those four lines, same length. And of course, opposite angles are equal. Now, do angles C and D? C and D are equal. But do they have to equal A and B? The answer is no. Imagine you open up this angle a little bit more. You open it up. And then you get something like that. But those two are the same lengths. These two are the same lengths. And since we have an isosceles triangles, these two angles are equal. And these two angles are equal. But there's no reason to assume that those are equal in one another. In the top case, they look bigger. Okay. So, having said what I just said, I'm going to put 2 slashes here. Okay, and of course, we know that those are equal. So basically, right now, I'm looking at the big triangle 1 up there and the big triangle 2 down here. And we have isosceles triangle. Well, actually, we don't yet. But I do know one thing. Opposite angles are in fact equal. So those two angles are equal to one another. Okay, so now by side, angle, side, congruent to side, angle, side, triangle 1 and triangle 2 are congruent. So now, corresponding parts are equal. In the top triangle, ABC, we know that these two are equal to one another, and we have an angle with 1 slash. And in the lower triangle, I guess I'm using C twice, I'm so sorry. Let's call the center of the circle O. We have CD, and we know the opposite angles are equal, and these two sides are the same. Okay, well, we know that angle A and angle B are the same. Well, what you do is you do 180 minus the 3 slashes. That tells you how much are left over for the other two angles. And since they're equal, you divide them by 2. But that's the same thing that's happening down here in the lower triangle. We have 180 degrees for the 3 angles, where one of the angles is the one with 3 slashes, and what's left over goes for C and D, but they get divided by 2. They're equal. So I can go back to the diagram and erase one of the slashes. I mean, you can also argue by corresponding parts of congruent triangles. C, D, A, and B are equal. Okay, so right now, so let me redraw this diagram because I drew one in a lot. And let us see exactly what we have. Let us see exactly what we have. We have a circle. I renamed the center O. We have AB. We have CD. And then I went like this, and I went like that, and like this, and like that. And we concluded that these 4 sides were equal. And we were given that AB and CD are equal. And then we realize that the opposite angles are equal. Let's give them 2 slashes. And that angle A, C, B, and D, those are equal. Okay. So we have this. But that's not enough. That is not enough. I need to show that the 2 chords are equidistant from the center. Well, there's something very special about isosceles triangles. And let me erase this and I'll comment on it. It has to do with their symmetry. You have a right triangle. Sorry. I'm suddenly not going to believe. Oh, okay. If you have an isosceles triangle and these 2 sides are the same. These 2 sides are the same. These 2 angles are the same. That means that if you cut it right down the middle, the left and right side are mirror images, which would mean that those 2 angles would have to be the same. And since it's 180 degrees, they both have to be 90 degrees. In fact, those 2 would have to be corresponding sides. So, when I go like this and I go like that, triangle 1 and triangle 2 and triangle 3 and triangle 4, since they were both the same triangles, basically, congruent triangles, when I cut them in half, all 4 of them are equal, which would mean that the corresponding parts, namely this side and this side, would have to be equal. Remember, they meet at right angles. Those 2 sides would have to be equal in length. That is, the chords are equidistant from the center. Is this distance in the upper triangle and the same distance in the lower triangle? They'd have to be the same. Okay, so those are the 2 main theorems. And it's not because somebody told you them, we proved it. So we can work out a couple of problems or a handful of problems and see what happens here. Suppose you have a circle. You have a triangle within the circle. You have the center, and you draw perpendicular lines from the center to two sides of the triangle. Let's just call it W, X, Y, R, S, and O. O for the center. So you are given some things. You are given circle O. You are given that OR is perpendicular to WX. You are, draw that a little bit nicer. You are given that OS is perpendicular to line segment XY. And you are also given that OS is the same length as OR. And you want to prove or conclude that angle W is actually the same measurement as angle Y. Okay. So, what do we have here? We're given, so I already marked that down. I labeled the circle O. So what else do we have? And the answer is we have that OS and OR are the same. So immediately WX is congruent to YX. The two chords have the same length. Why is that? Now, basically, for a moment, just ignore WY. What we have is two chords. I don't care that they meet at X down here. I don't care that they meet at the same point. If you have two chords and you go from the center to the chord, the first chord, and from the center to the second chord, and those distances are the same, the two chords are equal. Whether whether WY is drawn or not. Okay. So let's see what we can do here. I can draw that radius. I can draw that radius. And I can draw that radius. And basically, we have three triangles inside the big one. Here is the big one. And here's the center O. And now I have this. And of course, those are equal. Those are equal. Which means this angle equals that angle. And this angle and that angle are equal. And this angle and that angle are equal. Okay. So, let's call this 1 and 3 and 3 and 2 and 2. So we have angle 1 2 times, and then plus we have angle 2 2 times, and we have angles 3 2 times in the big red triangle. And this, of course, adds up to 180. Well, angle 1 plus angle 2 plus angle 3, whatever that is, it's going to be the same as 1 plus 2 plus 3 a second time. That is, we really have 2 times angle 1 plus angle 2 plus angle 3, which is 180. Well, that tells me that angle 1 plus angle 2 plus angle 3 is 90. Because I know one thing. 2 times 90 is 180. Okay. Now, maybe what we should do is introduce RO. So basically this was W, X, and Y, and now we introduce R and S. RO and SO. And these are right angles. So now we even have 2 more triangles. W, X. Okay. Remember, the center is O. If you look at W, O, X, this triangle here, actually these 2 triangles, this equals itself. You know, you're given that those are equal, and we have a right angle. By the high leg theorem, these 2 are equal. So in fact, WR and WX are equal. Now we can give the same argument in the lower triangle. X, Y, O, and S. We know we have a right angle. The hypotenuse both have 1 slash, and this, and we were given that these were equal to one another. SO and RO, or OS and OR, were given to be equal. These 2 triangles are exactly the same. Okay, so what does that tell me? That tells me that angle X and angle, why do I think that's labeled wrong? Okay, angle X, angle X and angle W, they're the same, and so are X and Y. So are X and Y. I think I did more than I needed to. Angle X and angle Y, all 4 angles are X, Y, and W. All 3 angles are the same. All 3 angles are the same because they're similar triangles. I guess I needed to do what I did. But yep, they're actually the same. I guess the one big thing I didn't need to do was this stuff down here. Those angles are the same. Okay, those angles are the same. I can argue that angles 3 and angle 2 are the same. Because if angle X equals angle W, if angle 1 plus angle 3 is equal to angle W, and angle 1 plus angle 2 is equal to angle X, then these 2 must be equal. these two are equal to one another. And if I take away the same from both sides, what's left over is equal. So I did prove that angle X and Y are actually the same. Just hack at it. Just write down intelligent statements. And statements that use geometry. Legitimate geometry. None of this made up stuff. Okay. Suppose you have a circle centered at O. And once again, you put a triangle. An isosceles triangle. A, B, and C. If I said isosceles, I meant equilateral. All three sides are the same. Okay? You are given equilateral, circle O. Oh, what am I saying? The circle is not equilateral. Equilateral triangle ABC inscribed in circle O. And basically what you want to conclude is you have a symmetrical circle, you have a symmetrical triangle inscribed in this circle. What you want to show is, what you want to prove is that AO is congruent to BO, which is congruent to CO. Now, just due to symmetry, if you just show those two, well then just rotate the triangle and then get that BO is congruent to CO. Okay, if you just rotate it. In other words, if I somehow show that AO and BO were the same length, well, if I rotate this configuration, and now I have B here, and, A here, and C over here, same center O, then I can say, from what I just did, remember, I showed that BO and AO are the same. But this is the same picture. I just labeled the points differently. Don't get caught up on that. Now, by symmetry, CO and BO must be equal. We now have that. So it's really enough just to show one pair are equal. If you don't want to show AO and BO are congruent, show AO and CO are congruent. And then you can say by symmetry, the third one is congruent. Alright, so now let me just remove these dashes because I don't know that they're equal. Oops. Use red. Okay. Now, what I do know is that BA, so basically I want to show what's in their box. BA is congruent to CA, which is congruent to BC. Property of isosceles triangles. This, and that, same lengths. And of course, those are equal. Those are equal. And that's all I needed. Why do I want to say that's all I needed to show? Oh, no. I want to show that. No. Of course those are equal. And I'll still stick by the symmetry story I said. AO, BO, and CO are equidistant from the center. Okay, so basically, I know that these three lines are the same. But, okay, so let me just clean this up a bit. Sorry about being a little bit sloppy. What I want to show is that AB and BC and AC they're all the same distance from the center. That is what I want to show. Okay. So, let us not worry about, say, this one. Let's not worry about that one for right now. In fact, let this be our diagram. Well, I want to show, let's label this something, X and Y. I want to show that those are the same. Well, the fact that AB and CA are the same length, they're two chords, same length. That means that their distances are equal. Okay? And that's it. That's it. That was a big McGiller there. Since AB and AC are the same length, why are they the same length? They come from an isosceles triangle. That means the distance from the center to AB and from the center to AC, those are the same lengths. And by symmetry, it's going to be true about BC. For example, BC and AC are two chords. Okay, they're the same lengths. That means if you go from the center to BC at a right angle, of course, or from the center to AC at a right angle, those distances will be the same. So I just use this theorem and it's pretty much a one-line proof. So one-line proof, or one concept proof. If we were going to formally write this up, statement, reasons, you're given equilateral triangle ABC. This is given. Number 2. AB is congruent to AC, which is congruent to BC. Properties of equilateral triangle. All three sides are, in fact, exactly the same length. Okay? And then you'll say that AB, AC, BC are chords in circle O. Why? Any line that goes from one point of a circle to another point of a circle is a chord. Any line that goes from one point of a circle to another point of a circle, that line is a chord. Okay, statement 4. And this is the theorem. The distance from O to AB, AC, and BC are all congruent. And basically, it's that theorem, that one of the two theorems we talked about. If three chords have 3 chords of the same circle, if 3 chords are congruent, then the distances from the chords to the center are all congruent. Okay, so that proof is done. If 2 or more chords in the same circle are congruent, then the distances from the center to these chords are also congruent. They come in pairs. Okay. You have a regular hexagon with the perimeter 24. With the perimeter equals 24. A regular hexagon with perimeter equal to 24 meters is inscribed in a circle inside a circle. What is the distance from each side of the hexagon to the center inside a circle? So basically you have a 6-sided figure inscribed. 1, just try to get a more round circle. One, 2, 3, 4, 5, and 6. Oops, what happened there? So sorry. Maybe I can draw it first. 1, 2, 3, 4, 5, and 6. Okay. And here is the center inside a circle O. The question is, what is the distance from the center to each side? Want to know how long is that distance? Well, first thing is we have 1, 2, 3, 4, 5. We have 6 sides. And if you take the perimeter, which is 24, and since it's a regular hexagon, hexagon means 6 sides, and regular means all sides are the same. 6-sided polygon, all sides the same length. So if I divide them by 6, you learn that each side is 4 centimeters. Okay? So they're each 4 centimeters. 4. Now I'm not talking about the arc, I'm talking about the length of each side. 4. 4. Okay. Well, let's consider this triangle right here. This is an isosceles triangle because those two sides are radii. Now, we know if we have a 6-sided figure, 6-sided polygon, the sum of the angles will be 2 less, 6 minus 4 is 2, times 180, which, if I'm not mistaken, is 720 degrees. But how many angles are there? There's 1 and 2 and an angle there, 3, 4, 5, 6. So if you divide by 6, you get that each angle is 120 degrees. But everything is symmetrical. Everything is symmetrical with a regular polygon. That is absolutely, that angle is 120 degrees. But you know what? This green line cut it in half. This cut it in half. 120 over 2 is 60. This angle right here is 60. This angle right here is 60. And this angle over here is 60. So let's look at this a little bit closer. 4, 60, 60, and this is also 60. That means it's equilateral. All 3 sides are the same. Okay? But I want to cut it in half. This is a right angle. That means this is 2 and this is 2. Let's look at the bottom half. Right angle, 60 degrees, 2 and 4. Well, Pythagoras can help here. Call this x. 2 squared plus x squared is equal to 4 squared. This must be 12. 4 plus 12 is 16. That is, x squared is 12. So x is the square root of 12, which is the square root of 4 times the square root of 3. The largest number that I know the square root of that goes into 12 is 4. That's why I said 4 and 3 and not 6 and 2. I don't know the square root of 6. I don't know the square root of 2. 2 square roots is 3. And that is the answer. 2 square roots is 3. This black line, which is now red, is 2 square roots is 3. 2 square roots is 3. since all the chords are the same length, it follows that each of these distances at right angles must be the same. They're all 2 square roots of 3. Let's try one more. Know their 2 theorems and know how to apply them. Here we have, again, a triangle inscribed, and this triangle happens to be isosceles, ABC, with AB and BC, AB and AC, they're being their congruent sides. So let's write this down. What are you given? AB is congruent to AC. And let us just call the center O. You're given that AD AO. Oh, it's not true. Let us have from A, let's go through O straight down. Call this point of intersection D. So line segment AD is perpendicular to line segment BC. And another point, OF, is perpendicular to AC. Here's F. And you are given that AF equals C and EO is 1. FO is 1. FO is 1. Okay. So you were given that AF is 1. How about 6? Excuse me. AF is 6. And FO is 1. And you were, let's see, given AB and AC are congruent, and AD meets BC at right angles because they're perpendicular, and you are given another perpendicular here. And you want to find the radius of the circle. You also want to find the perimeter of triangle ABC. And I guess we're going to use Pythagoras to find the radius, because if you look at this triangle over here, the one that goes from A to O to F, it is a right triangle. Let's put A here, excuse me. It is a right triangle at F. So right triangle at F, AF is 6, and OF is 1. So AO squared, which is a radius, is equal to 1 squared plus 6 squared, which is 1 plus 36, which is 37. So if r squared is 37, r is equal to the square root of 37. And none of the numbers other than 1 that I know the square root of, I know the square root of 1 is 1. Other than 1, no number that I know the square root of goes into 37 evenly. So I can't reduce it. Okay. So now we need to find the perimeter. We need to find the perimeter. So what I know now is that distance is the square root of 37. Okay. And of course, this must be 6 as well. Well, it doesn't have to bisect it. If you have a chord and you have a center, when you go to the chord, doesn't have to split it in half. And the answer is yes. The answer is yes. It's got to split it in half. There's no way around it. It bisects it. Okay. So now what I know is, remember, AB, which is 12, 6 plus 6 is 12. Sorry, AC is 12, so is AB. This whole length is 12. And again, 6, how did I get 12? 6 plus 6 is 12. I'm almost done. It's 6 plus 6. Now I need to know BC. I need to find out BC. Also, an isosceles triangle is cut straight down by A. I know these two are equal. I know those two are equal. The question is, what does it equal? 12, 12. Let's draw this again. Let's see what piece of information we didn't use. And let's keep in mind these two theorems that we were given in this section. So we have an isosceles triangle which has symmetry. That is, when I cut it right down the middle, that is when I cross the center O, I know that these two sides are equal and I have a right angle. I now know that's 12 and this is also 12. But if I go like this, I know this is 6 and that's 1. And of course that's 6. That being this. And that piece is the square root of 37. Okay. Now, what I know is that we have a chord down here. We have a chord down here. And that this line this line met at a right angle. That means, so do I have any equal chords? That's what I want to think about now. Well, let's just label this B, C, and A. I know that AB and AC are equal chords. So that means this distance is 1 as well. But does that really help me? What I do know is, and I don't see how this is going to help me, I do know that this line and this line are the same lengths. Not seeing this one. Well, I know that the radius is square root of 37, so these are both, not 6, but these are both square root of 37. This is square root of 37, and so is this length, the square root of 37. Now, if it was an equilateral triangle, I would know this length is 1 as well, but I don't. I'm not given that it's equilateral. So basically, I just need to know how long this is, or how long this is, or how long the whole thing is. That's all I'm waiting for right now. Okay. Let us use the little triangle 1 here, and let's call this distance x, and let's call that y. And we're going to come up with 2 equations or 2 unknowns. Using that little triangle, we come to know that x squared plus y squared is square root of 37 squared, which is 37. Now, let us use a bigger triangle. Let me draw it over here in red. Let us use this big triangle. We're calling this y. We know that's 12, and we know from the center up is square root of 37, and from the center down to D, I'm calling that x. We have 12, we have y, here's the center, this is square root of 37, and the rest is x. So this whole side will be x plus square root of 37. And when we square it and add on y squared, we should get 12 squared. And when I square the left, I get x squared plus 2 square root of 37x plus 37 plus y squared. Now y squared, bring that to the other side. Y squared is really 37 minus x squared. That's y squared. and this still equals 144. The first thing is x squared minus x squared is 0. So I have 2 square root of 37x plus 37 plus 37, which is 74. When I take it away from the other side, I get 70. So that must be 35. 2 times 35 is 70. The square root of 37, the square root of 37x is 35, which means that x is 35. Actually, I don't want x, I want 2x. I want 2x. Actually, I want 2y, excuse me. Okay, so what I was doing is correct. X is equal to 35 over the square root of 37. So that's x. Now, I need to find y. But we've already said that y squared is 37 minus x squared. And this will give us 37 minus 35 squared is 1225. 1225 over the square root of 37 squared, which is 37. Let us do some arithmetic here to find out what y squared is. I want to get common denominators. So it's going to be 37 squared minus 1225 over 37. I multiply top and bottom by 37. And 37 times 37 is 259. 37 times 3 is 111. And when you add these, you get 1369. So we have 1369 minus 1225 over 37. And this difference is 144, it looks like. 144 over 37. That is what y squared equals. So y is equal to the square root of the top, which is 12, divided by the square root of the bottom, which I don't know. And now I am ready to give the answer. The longer-awaited answer. What is the perimeter? The perimeter is this distance, which we claim is 12, the perimeter of triangle ABC, plus this distance, which is also 12, plus y plus y. Well, y is equal to 12 over the square root of 37, so 2y would be 24 over the square root of 37. And there is your perimeter. That finishes the section on chords, congruent chords.